Hey, welcome to Wednesday, week 3. Alright, so assignment 1, where's Whale? He's meant to be working on it. Perhaps that's where he is. He's at home, writing a sample solution. Good. Out soon, due at the end of week 6. And the problem is going to be, you know how you go into shop sometimes and you see that text scrolling across, grungy looking ASCII characters, so that's what you've got to do. Typically that's the kind of thing, well actually nowadays it's probably written in C or something equivalent, but back in the good old days it would have been written in MIPS, so that's what you're going to do. So we'll give you big chunks of MIPS code, the sort of wrapper around everything, and you have to write a couple of MIPS functions to implement the actual scrolling part. Alright, there'll be another quiz next week, due at the end of the week. Alright, so today I'm going to say more about MIPS assembler and start talking about how you might write MIPS programs. And my argument is don't sit down and try to write directly in MIPS. You write a C solution and then you translate that into MIPS, and I'll show you how to do that. Alright, here's another nerdy thing. Once again, we're back in the 40s. This is one of the first stored programmable electronic computers. This one was, I think, done at Manchester University just after the Second World War. And it's called Manchester Mark I. So, to give you some idea about how primitive things were back then, apart from the fact that all the photos are in black and white, that's not a stylistic thing, it's just the way things were. So, 4,000 valves, woohoo! The memory, 128 words. How are you going to write programs that fit in 128 words? Interesting prospect. And the massive amount of storage, 1,024 40-bit words. Whoa, can't fit much of a file system on that. And it didn't really matter because the storage media wasn't particularly useful as a file system anyway. 30 instructions, well that's not so unusual, and really the reason for that is you don't need that many instructions. As long as you can add, as long as you can test, and as long as you can jump, you can pretty much build any computable function using that. It wasn't particularly fast either, and you had to program it by flipping switches on the front panel or by putting some holes in a paper tape and feeding that in through a paper tape reader. So think how lucky you are that you can sit there with your keyboards and your mice and your pointy, what do you call those things, iPads, and do stuff with GUIs and the like. Oh yeah, that's right. One thing that cropped up when I was sitting at home last weekend, getting all this email, my program doesn't work. What do I do? Here's some output. That's not what you're supposed to do. And you're not supposed to do it because you need to develop these skills to solve those kind of problems. And I would have hoped that you might have developed some of those skills in COMP1521 or 1911 or 1917, whatever your original programming course was. You need those skills because they're going to help you get the labs done. But in the labs you can always ask the tutor. And the tutor will sit down and they'll work through the process with you probably, unless they're a rude tutor and they might say do it yourself. It'll help you with assignments, but once again you've got a bit of assistance with the debugging task. But one place where it's going to be critically important that you can solve debugging problems yourself is in the final exam, because you're not going to be able to say, hey, my program doesn't work, help me, what's wrong? No one is going to help you, you've got to do it yourself. And debugging, as soon as you write any code, once you've left this place, you're going to have to debug it yourself. You can't go and ask your manager, oh, my program doesn't work, what do I do? He'll expect you, or he or she will expect you to work it out yourself. So, here's a very quick overview. People have asked for GDB, people have asked for qtspim. I'm not going to talk about GDB now because we're going to spend the next couple of weeks playing with MIPS. So I will have a bit of a look. I want to look at qtspim today to give you an idea how to use that. But the process is essentially the same whether you're debugging MIPS or whether you're debugging C. And the basic idea, and this little cartoon gives the idea away nicely, you've got to look at the program and you've got to study it in detail to work out what's happening. So in a sense it's like detective work. So if you're a detective, you end up at a crime scene, there's a dead body on the floor, you've got to look around, are there bullets, is there a knife covered in blood, blah blah blah, whatever. To try and work out what happened, and then maybe there's some clues about who might have committed the crime based on fingerprints on the knife handle, whatever. Similarly with debugging, right, sure, look at the output and it shows you, a bunch of numbers from one array when you're expecting numbers from another array. Well, possibly in your printf statement you put the wrong array. That would be a very simple mistake to make and very easy to fix. Or perhaps you've overflowed one array and you've scribbled on top of the other array. Now if you're using DCC, that'll pick that up. If you're using straight GCC, it won't pick that up. It'll just let you scribble over the top of your second array, and you will have to work out exactly what's happening. Alright, so always the idea is that you take some observations and then you come up with a theory of what might have gone wrong. So that example I just gave, where part of the output from one array looks like what should have been in the other array, a hypothesis is, oh, I overflowed the end of the first array and it started scribbling over the top of the second array. Next thing to do, start looking for clues that will help you establish your hypothesis a little bit better. And in the case of debugging programs, look at the code. So, is there something funny? So, I've obviously put some stuff into an array. Look at the index, look at the loop that went through and filled up that array. Is the array bound correct? Am I doing I++ correctly? Am I using I, the index, correctly? There's all those kind of things to look at to try and give you a bit more fine-grained idea of what's going on. Then, a very useful thing to do with debugging is to run the program again, but this time rather than just letting it run and letting it produce output and then trying to work from the output, watch what happens when the program executes. To do that, you're going to need some kind of debugging tool, or you can just stick a bunch of printf statements in the program. So you've got to be able to observe precisely what the program's doing, what are the values of the variables at particular points in time, and you might discover in the case that I was talking about that you've used the wrong bound on the for loop. So instead of saying for I equals 0, I less than n, you said for I equals 0, I less than m, where m is the size of the other array. Okay, so you've overflowed the array. So if you happen to notice that the value of I, let's say m and n is 10, m is 20, so I equals 0, and then you observe I equals 1, I equals 2, I equals 3, I equals 4, I equals 5, I equals 10. You shouldn't see I equals 10. It should stop when I equals 9, because it's probably going to say I less than 10. So as soon as you see something like that, which is an anomaly, you know what's gone, or you should be able to work out what's gone wrong then, and then you can fix the problem. So that's really the essence of debugging. I'll show you a lot more examples of how this plays out in practice. But all right, you have an initial observation, You try and formulate what might have gone wrong. That's your hypothesis. You look at the code to see if there's something in the code that confirms what you thought. If you can't observe anything, and this is quite frequently the case, you look at the code and what you see and what's actually there is sometimes quite different, because you've got ideas in your mind about what that code should be doing. What you actually wrote in the code isn't quite the same thing. But when you look at the code, you think, yeah, that looks right. One way to do debugging, which you can't use in an exam of course, is just to ask someone else to have a look at the code. And usually they'll come along, they'll look at the code, and straight away they'll spot the problem, because they're not coming to look at the code with all the preconceptions that you've got in your head that developed while you wrote the code. Okay, so that can be, and this is why tutors look so clever, because they come along, they look at your code and they go, aha, that's what's wrong. And the reason is, you're looking at it because you think you wrote an N there and you actually wrote an M, and you think, yeah, that looks right. They come along and look at it and straight away they see, no, that's not supposed to be M, it's supposed to be N. If you can't work out what the problem is, start running the program being sensible about where you set up observation points. Now you can't print out the value of I every time through the loop. That's going to produce a whole lot of unnecessary values. Maybe you can, especially if it's a loop that's only going 10 times or so. And as soon as you see that I is greater than the upper bound of the array, then you realise what the problem is. But being a little bit sensible about where you observe the program, and a lot of the time what you're going to need to do, especially in a slightly larger program, is run it for a bit and then stop it at a certain point. So setting a breakpoint, making it stop on a call to a particular function, and then stepping through the function to see what are the parameter values to the function. Do they look correct? Go into the function, what's the value of this variable? Does that look correct? Execute the next statement. Do all of the variables look correct? Execute the next statement, and so on and so on. And once you do that a bit, you're guaranteed to find out what the problem is, and then you can change the code to fix it. So by the end of this course, I'm kind of hoping that writing a C program or a MIPS program, even if it's got a bug in it, you can work out what the problem is and fix it by doing this kind of thing. Alright, let's get back to MIPS. Right, just to recap a little bit, so MIPS is a machine architecture. What MIPS means, I've forgotten already, despite the fact that you told me in the last lecture, something to do with pipeline, blah blah. But so MIPS is an architecture, and part of defining that architecture is to define an instruction set. So that's what MIPS is. And, oh damn, I was going to take a photo. When you walk into K17 through the ground door, you may notice, well, straight in front of you there's a garden, but just off to the left there's a big fridge-like box with, may have Silicon Graphics written on it somewhere. That box contains a MIPS processor. So, they still exist, although admittedly that box is there as a museum exhibit, but once upon a time it was a viable computer. In any case, so MIPS is a machine architecture, it's a piece of hardware. SPIM is a piece of software that simulates the behaviour of a MIPS CPU. And it's a little bit different to the MIPS CPU. The MIPS CPU reads in binary code and executes according to that. SPIM can read in symbolic assembly code, do a simple translation, so it's nothing like a C compiler, which does a lot of work and produces a lot of extra code compared to what you wrote in C. Here there's a very close correlation between what you write in your SPIM assembler and the machine. So what SPIM does, reads that assembly code, turns it into a binary form which is very close to what you originally wrote, but in binary, and then executes the binary code. However, unlike unlike a MIPS CPU, it allows you to do things like single step and to look at the contents of registers as you go. SPIM itself will let you do things step by step, but it's a lot more obvious what's going on when you use something like qtspim or xspim. And also, because you're running SPIM on top of Unix, then you've got to have some way of interacting with that, you know, reading stuff in, writing stuff out. So there's this syscall instruction that does that for you. SPIM provides a number of extra instructions which aren't technically MIPS instructions, but the SPIM interpreter or SPIM emulator converts them into raw MIPS instructions. So for example, there's an instruction to copy values between registers. So I can write move from $V0 into $S0. Okay, so that's like an assignment statement in C, but between two registers. That's not actually a MIPS instruction. The way MIPS would do it, it would take V0, it would add 0 to it, and then store the result in register S0. So if you take a value and you add 0, you get the same value, you store it in S0. So it gives you exactly the same effect as doing this. And the fact that it's add U is add unsigned. Okay, so you can either treat the contents of a register as a signed int or an unsigned int. So the fact that we don't really have a move instruction means that the hardware can be simpler. We don't have as many different instruction codes to deal with, and we can exploit things like this to produce exactly the same result as this. And it's also helped by the fact, if you remember, I said last time that register 0 always contains the value 0, which turns out to be useful in this context. All right, so SPIM is a process that you run. You can load a program into it using the -file option. So SPIM -file, the name of your MIPS assembly file. That will execute. You can use syscalls to read stuff from standard in. You can use syscalls to write stuff to standard out. And you can actually access argc and argv. And there's something like an exit. One of the syscalls actually halts the program, which is more or less what exit does in a C program. So that's command line tool, if you like. It's a batch thing. It's not technically not interactive. You feed in a program, it runs the program, and then it stops. Now the program might happen to do some input and output, but not necessarily. On the other hand, the two GUI tools for dealing with MIPS programs, qtspim and xspim, involve you extensively. So you run, I'll just use qtspim as an example. You load up a program using one of the buttons at the top of the tool. That loads the program into memory. You can see what the program looks like when it's loaded into memory. You can see what all the registers look like, and then you can run the program statement by statement if you want, or you can just execute it. And if you execute it, it'll pop up a console so that you can do input and output. But the critical thing is you can see in great detail what's happening in the registers. If you want, you can even look at the memory. Most of the time it just shows you the instructions in the text segment of the program. But you can flip and have a look at what's going on in the memory as well. So you can see everything. It's like a transparent machine. Alright, so what SPIM gives you, it gives you the basic MIPS instruction set, plus these pseudo instructions, and even things that look kind of very simple, load immediate. It's not a real MIPS instruction, it's implemented using some of the real MIPS instructions, and I think last time we saw that load immediate was actually implemented using an OR instruction. Branch greater than, that instruction actually turns into two MIPS instruction. One is do the comparison, and the second instruction is based on the comparison, either transfer control of the execution to some other part of the program or go on to the next instruction. So it's not even just one instruction that you get from doing that. And you can see this becomes really clear if you have a look at qtspim, which we'll do in a minute. Alright, there's also directives like .data, .word, .space, which allow you to define data structures, and there's a syscall that allows you to interact with the outside world, plus the tools that we just looked at. So that's the SPIM environment, if you like, the SPIM ecosystem. Right, so what syscalls have we actually got? So as I said last time, we don't have a standard I/O library. We've just got these very simple things. You can talk about them as if they're functions done by the standard I/O library, but you've got nothing like printf, you've got nothing like the full generality of scanf and printf. You've got very restricted sets of what printf and scanf do. So you can print an int, so that's basically like printf quotes %d, and that's all you've got from that. You can print out one integer value, you can print out a floating point value, you can print out a double length, double precision value, you can print a string. Like I said last time, most of the time we're not really interested in floating point when we're dealing with MIPS, so mainly what you'll be doing is printing numbers and strings, and you can also read these things in as well. So clearly with a print, you got to supply a value that needs to be printed. Where do you put that value? You put it in $A0 if you're talking about an integer or a string. You put it in the floating point register F12 if you're talking about a float. So you have to put the value somewhere, and then you invoke the syscall by giving the code for the syscall and putting that in register $V0. For read functions, clearly the idea is you say, I want to read in integer, I've got to store it somewhere. Where does it end up being stored? It ends up being stored in the V0 register, which, if you remember from last time, V0 and V1 are two registers that are defined by convention to be used for returning the results of functions, or in this case, returning the result of a system call. Similarly, so if you do a read string, you have to supply two parameters: the name, the address of a buffer where you want to read the string into, and the length of that buffer. And read string will read characters from standard input up to the end of a line and store them in that buffer, and it will append a new line like fgets does, and it will also append a null character like fgets does. So in some sense, read string behaves a lot like the fgets function that you got in C. What about these pseudo instructions? As I said, load immediate isn't done, it's not a real MIPS instruction. That's how it's actually implemented. So you take the constant value, you OR it against 0, and that produces a result which is stored in some register, in this case T5. Loading an address ends up with two instructions because addresses can be 32 bits long. Clearly, this value here can't be 32 bits because some of the 32-bit instruction is used for those two things. And I think if you remember, the instruction code is 6 bits and the destination register is 5 bits long. So you've already used 11 bits of your word, so clearly you can't have a 32-bit quantity here. So it does this. So it understands what this address is, and it takes the top 16 bits of that address and loads them into a temporary register, and then takes the bottom 15 bits of the address and ORs that with the top 15 bits, top 16 bits, sorry, that you put into the register AT, and stores the overall result. So here, you're basically taking a chunk of bits that's the high order bits, another 16 bits that's the lower order bits, you're ORing them together, that'll give you a 32-bit result, which ends up in T3. So 2 instructions, but it's way easier to think of it like that. The only time you really have to deal with this stuff is when you're, for example, looking at qtspim, you actually see these instructions rather than this one. This one appears, but it appears as a comment. This is what actually gets executed. Right, so a branch instruction, branch with condition. The basic idea with these kind of instructions is you do a test, and if the test is true, you want to transfer control to a particular location which is defined by some label. So these are the 2 values in the test. Notice all of the MIPS operators are basically binary. So if you've got, if you want to check whether x plus y is greater than 5, then you'll first of all have to compute x plus y, store that in a register, put 5 into another register, and then you can do a test like this. So what actually happens here is we do, the first instruction that gets produced is SLT, which basically stands for set the status of a less than test. So it performs a less than test on these 2, the value stored in these 2 registers, and stores the result once again in this $AT register, which I mentioned last time is basically a register that's used by the assembler. User programs generally wouldn't touch this register. It gets used in contexts like this. In any case, so we do the test on these things, check whether T1 is less than T2, and we store a result in here which is either 0 if T1 isn't less than T2, or non-zero if it's greater than or equal to T2. So the next instruction is a genuine branch on condition, but it's a much simpler one than a BGE. It's just doing an equality test. So if the status that we stored in register AT was 0, then we transfer control to the label, to the address at that label. And similarly for branch on less than, we do a less than test once again, and in this case we're checking for less than, so we want to make sure that the result of that test is not equal to 0, okay, which means true. So branch on not equal to 0 to the label. But like I said, you don't generally need to think in those terms, you can think in these terms, which makes programming a little bit easier. And there's other branch type instructions. Branch on equal is actually a genuine instruction that you can use. If you want to test whether the values in 2 registers are the same, you can use that instruction yourself. Branch on not equal, branch on greater than or equal, that's what that is. Branch on greater than, branch on less than, branch on less than to equal, less than or equal. All those instructions exist as pseudo instructions. All right, the other thing that SPIM assembly language provides are directives. .text, I mentioned last time, says everything that follows that is, you're expecting it to be code, so it's put in the code segment of the memory. If you have a directive like .data, then it says everything that follows, I'm going to treat it as data and put it in the data segment of the memory. You can use this directive to make a particular label globally available. You can give a name to a piece of memory by giving a label followed by a colon, and then what this directive does, it effectively says, all right, I've got 18 characters, so I'm going to allocate space for 18 unsigned chars. So by default, the system's going to treat most things as unsigned. So That's the way you can think about that. Or if you wanted A to be an array of 4 integers, then you'd still allocate it using space 18. Now space 18 is a bit silly value. 18 is a bit silly value to use in that context. You're better off using 16, which is 4 times 4 bytes. But in theory you could use 18. You can specify alignment. I've talked about alignment a bit. You can't access objects in the memory. You can't access an int object using an address that's not a multiple of 4. You can access a byte object using any old memory address, 1, 2, 3, 4, 5, 6, 7, whatever. To access an int, the address has to be something like 4, 8, 12, 16, and so on. You can allocate space and store constant values in that space, so that's what that directive there does. You can allocate something that looks like an array by specifying multiple values. So these are kind of the C equivalents of what I've written over here. MIPS and SPIM understand 3 kinds of data, if you like. 4-byte data, so that's the size of a register. 2-byte data, so you can grab chunks of 2 bytes from memory, store them in one of the registers, and individual bytes. So 8 bits, 16 bits, 32 bits. So you can manipulate data in all of those kinds of quantities. So if I want to have an array of 3 chars, where those chars aren't particularly interesting, because they're all non-printing characters, those ASCII codes 1, 2 and 3, but you could do it, so you'd end up with saying B is a label associated with a sequence of 3 bytes, and those 3 bytes are going to contain the value 1, the value 2 and the value 3, so you'd end up with something like that. And similarly you can do floats, and you can do strings of characters. Using .ASCII-Z, null pads the string like C does. If you just say .ASCII, you don't get a null padding on the string, or you don't get a null terminator. So that would be, unless you also happen to keep track of how many characters you'd stored in that buffer, or that you knew the size of the buffer, you want to be a little bit careful using that .ASCII. Alright, so last time we wrote a program to add up 2 numbers. The numbers were stored in the memory, so there wasn't any particular interaction apart from writing the result out. Let's change it up a little bit and print out, print out a prompt, ask for a number, read in a number, ask for another number, read in the second number, add them up, and then print them out.
Dr. Shepherd.
Yep.
My name is Raymond.
Yeah, I know.
Alright, good. So what's the difference between directives and MIPS instructions?
Yeah, a directive is something that specifies data, basically. Some of them also give a hint to the assembler where particular things should be located in the memory. So if you have .text, you're typically going to have that at the start of your code, and then when the MIPS assembler reads all that code, it sticks it in the code segment. As soon as it sees .data, anything that comes after that is going to be put in the data segment. Now if you were silly, you could put .data and then put your program, and what would happen is that all the binary codes for your program would end up in the data segment, which I don't know if that's particularly useful, but you could do it. But basically all of these kind of directives down here allow you to define data. Okay.
Thank you, Dr. Shepherd.
Alright, so rather than writing it from scratch, I already wrote it. Right, so And here, this is also an example of how you take a program written in C and convert it into MIPS assembly. So this is, I think, the original program that I had on the slide. Maybe I had these things as local variables, but I can make them global variables if I want by putting them outside the main function. Right, so we want to print out a prompt, read in a number, print out another prompt, read in a number, then add them up and print out the result. Now I think we saw last time that you can't do something like that in MIPS assembly. You can't mix up printing out numbers and printing out strings, and that, if you like, is a simple string. Okay, so you've got to do those as two instructions. And in fact, in general, any C statement that you write is going to turn into multiple MIPS instructions, maybe 2, maybe 3, maybe 4, and it may include pseudo instructions, in which case they'll be expanded even further. So a single C statement could turn into 5 or 6 MIPS instructions. Right, but let's have a look at this. So here we're defining all our data stuff. X is an integer, just occupies 4 bytes, that's all we're saying there. Similarly, Y is an int value which occupies 4 bytes. We're not actually, MIPS doesn't really have a clue that it's an int. All it knows is that it's 4 bytes long. So hey, here's a 4-byte object that I'm going to do something with. So you can see that in C we can write the strings directly in the program. In MIPS, you have to do what the C compiler does for you. So if I write this in C, in a C program, it's going to take that string and stick it in the global data area. I think I showed that once or twice when I was talking about those regions of memory that the C compiler uses. So that would get stored in the data segment, if you like. In MIPS, you have to do that explicitly. You have to do it yourself. All right, so since here we didn't have a name for this thing, we've got to give it a name, so I just called it ask1. Similarly, for second number, we stick it in the data segment, and similarly, this thing here also has to be stored in the data segment by us, so we don't have the C compiler helping us out for that. All right, so that's the setup for all of the data, and here I've written down more or less what would be an equivalent C instruction. So rather than writing first number in line, I actually have to effectively define a variable and associate that variable with the string. And of course in C I'd have to put semicolons at the end of the lines, but be that as it may. So that's all about data. What about the code? Right, well, the first thing we would want to do is we want to print out that prompt to enter the first number. So to do that, we need to do a syscall. If you look back at the slide on syscalls, the syscall for printing a string, or the code for the syscall to print a string is 4. We have to load that into the V0 register. This is just fixed. You know, if you want to do a syscall, you say what syscall you want to do in the V0 register. And if there's an argument to the syscall, like there is here, we put it in the A0 register. That's just the way syscall works. Or it's the way this syscall works. So we need to, and this, this is interesting. So if you look in the original C code, you can see that we have to specify the address of X, because the intention of the scanf is to change the value of X. So we have to pass in a reference to the X variable. So how does all that play out here? Well, first of all, we obviously print out the prompt like that, using that syscall. Then syscall number 5 is readInt, so read in a single integer value. So we load up the 5, we make the syscall, the result ends up also in register V0. So you can see V0 is being used for two totally different purposes there. One is to set up which syscall we're making, and after the syscall's happened, it's used to hold the return value. All right, so if we want to take that return value and store it in the variable x, we have to do it explicitly like this. So this syscall is never directly going to put something into the memory. It's always going to put whatever you read in register V0. So then we've got the value we wanted in V0. The goal was to store it in X, so we can use the store word instruction to copy the contents of register V0 into the memory at this location here.
Dr. Shepard,
So that, yep.
you're putting some, just before you have the dot data,
Yeah.
for this, yeah, and then so what goes into the data?
Directives that define data structures, which is what all of these things are.
Alright, directives that define data structure.
Yeah.
And text,
Is where the code goes.
where the code goes.
Yeah.
Alright.
So you can see dot text, and then I've got all the code. If I didn't put that dot text, all of this code, or all the binary for this code, would end up in the data segment, and I wouldn't have a program in the code segment that I can run.
Alright. And what does syscall do?
It's a special instruction that allows the SPIM interpreter to interact with Unix.
Allow Spim to interact with
Unix.
with what, sorry?
Unix. Unix.
Unix?
The operating system that
Alright,
we're
operating
using.
system.
I hope.
Alright, thank you, Dr. Shepard.
Okay, so print out the prompt, make a syscall to read in the integer. It always ends up in V0, so we have to copy it to the variable x. Now here, it's a little bit of a waste of time copying it into memory. All you're going to do, as we'll see later on, is load it back in. So how you handle variables is an interesting question when you're writing MIPS code. A lot of the time I would suggest that you should do variables in registers rather than putting them in memory, and every time you change the variable, you load its value into a register, you manipulate the value in the register, and then you copy it out to memory again. It's generally better to allocate a particular register as representing a particular local variable and do everything through that register. Now you might say, hey, I've only got 16 registers, so I can only have 16 local variables. How many of your programs have ever had more than 16 local variables in a given function? I would guess not many. So having 16 registers to play with is probably good enough to implement most things. But here I'm being really explicit about the fact that X is an object which exists somewhere. It's a global variable, so it's got to exist somewhere in memory, and every time I want to set the value of X, I have to create the value in a register and then store it into X. So that set up the value of X. Then print the second prompt using syscall 4, read in the value using syscall 5. Once again, the value that I read in ends up in register V0, and then I want to copy that value into the memory that corresponds to the label Y. So in the C code here, I've assumed that I've got variables with the same names as the registers, and so I'll just use them like that. So imagine, somewhere there's a local variable A0, there's a local variable V0, and so on. Alright, so I've read in the two values. The first value I read in is stored in the memory location with label X. Second value is stored in the memory location with label Y. I then want to print out the sum of those two values. So in the C code, let's jump back up here. That's how I do it, a single instruction which combines the idea of adding the two values together and then feeding that into a print statement that prints out a number and prints out a new line character. In MIPS, it's a little bit more messy than that, or a bit more fiddly than that. We need to load the two values from the memory back into the registers. It's the only place you can manipulate data, modify it, add things together, whatever kind of instructions you want to do. So we load X into register T0, load Y into register T1. Why did I choose T0 and T1? Arbitrary choice. I could have chosen T1 and T2, or S1 and S2, or S0 and S7. Doesn't matter, as long as they're two different registers. Here I'm trying to minimise the number of registers that I actually make use of. So T0 and T1 contain X and Y. Then there's an add instruction which adds them together and stores the result in A0. Why did I store it in A0? Because A0 is where I need the value to be so that I can print it out. I could have done add T0, T0, T1, which would have effectively done T0 equals T0 plus T1. And then I could have moved the result that I got into A0. But why do that when I can do it in a single instruction? So that sets up the sum that I want to print out in A0, and I then set up the print a number syscall by loading 1 into V0, and then I do syscall. How do I know it's 1? Basically, I've got to keep going and looking at this table here. So I know I want to print out a number, so I look for what I want to do, the operating system service I want to make use of, and I discover that code 1 is what I need. Alright, and so print out that single number. Next thing to do is to print out the new line character. So I can't do it all at once. That's effectively as much of a something like printf as I can do. Printf with a single value of some type, and then you give the value. Alright, here I load in a pointer to the string. I should have pointed that out before. Here I'm loading the address of the ask_to object, because if we go back and look at these, if I want to do print string, I've got to pass in a pointer to a character, a pointer to the first character in the string that I want to print, and MIPS is going to assume that there's a null terminator at the end of that string. Okay, it's the same kind of thing as happens in C. So I load in the address of the string containing the single end of line character, \n. I set it up to print a string, which is syscall code 4. Then I'll make the syscall, and that'll print out the string containing the new line character. And then that's the end of main. Normally, in a C program, you'd return from the main. The way you do it in MIPS is you do a jump to the register RA, jump via the register RA. So take the contents of RA, use that as an address, and then go to that address and keep executing. So basically, you go there's a little chunk of code that calls the main program. What this does, it goes back to that chunk of code, and that chunk of code cleans up and then calls the halt function to stop the program running. So, how does this all work in practice? Oops, I wanted to stay in that window. So here's one way I can run it. Right, so it's printed that string first number. I can type in the number, let me see, 25. I could type in the second number, 999. So it's going to take those two values, add them up, and print them out, and print out a new line character afterwards. If you do, that's a lot of a fair amount of MIPS code compared to the size of the original C program, but that's life. Assembly code is always larger than the same code written in a high-level language. Alright, having a look at how that runs in qtspim. Alright, so let's fire it up again. This text is a little bit small, maybe. Doesn't matter. Alright, so up here we've got the user text segment, which basically means where the user code lives. The system has already stuck some code there for me, and this is basically the little function that calls the main program. So you can see here we've got a jump and link to main. Jump and link I'll explain in detail how that works later. But basically it's make a function call to that. One thing you might notice if you look over here, so actually may as well point out everything we've got here. qtspim will put your original code in a comment. In this context they use semicolons to start a comment. Then it will print the MIPS instruction that it's actually going to execute, and it will also show you the binary for that instruction. Now you might say, hey, there's no main program. My main program can't be at address 0 because that's not a valid address. The actual code, if you remember what I said last time, starts at that address there. So we need to load the program in. All this code down here is stuff provided by the kernel, the operating system, which we don't have to worry about. So what we need to do is get the code. Oh, where'd that go? IAD was the one. And now you can see there's a fair bit more code than there was. It loaded very quickly. So the user text segment, remember that this thing used to be jump and link to 0. Now it's jump and link to an actual address where the main program has been loaded. So that's the address where the main program ended up. And you can see it comes straight after the code that was already there. So it's just taken the machine code for the IAD program and just stuck it into the code segment after whatever was already there, which is that. So this is the actual code corresponding to the MIPS that I wrote. There might be even more. Yeah, all the way down to the jump on the register. So this is what the machine code, or the hardcore MIPS code that's produced from what I wrote as, if you like, spin code. So some of the instructions, like for example load address, end up being done as two MIPS level instructions. Load immediate forward is implemented not by some load immediate instruction but by an OR immediate instruction. Syscall and once again load immediate 5 implemented by OR. Loading the address is alright, this is interesting. So this is how we've produced store word v0 into x. Okay, so remember x was an object that I defined in the data segment, and if I want to look at that I can actually go and look at the user data segment, which I'll discover is located somewhere up here. And here you can see the strings that I've put in. Those .ASCII produced this code. So these are a whole bunch of ASCII codes stuck into the data region of the program. And the first string extends that far because you can see that the last byte is 0 0, which is the null character. So that's the end of that first string. Then the second string starts and goes to where? Interesting question. Goes to there. Yeah. All right. So where's X? Where's Y? X and Y, I would guess, are in this part of the data segment up here. Yep.
I'm just wondering which part corresponds to the load immediate, load zero.
Yeah.
And that
Nothing here corresponds to that because that's an instruction. What were you talking about? There's plenty of load immediates, so there's that one there. So we want to load immediate 4 into $V0.
load immediate 1.
Alright, but where's that? We don't have a load. Do we have a load immediate 1 in the program?
It wasn't the code that you wrote.
Really? Oh, yeah. Where's it gone? So read, it's a long way down. Alright, down here. Yeah, you can see how much code is being produced from my few lines of MIPS assembler. So that's how you do load immediate 1.
What is the best way to identify which part corresponds to which part? That makes sense.
Yeah, look at the comments down here. So these things here, as I said before, these things correspond to the code that I wrote once we get beyond here. So that's all main program. Okay, and so the first thing in the main program was load the address of ask1. Okay, if we go back to the code itself. Oops, no, that's right. Nope, too far. Right. So the first thing we do, load the address of ask1 into A0. Register A0, that's interesting. Oh yeah, alright, so load address ask1 into A0. So, what it's actually doing, it's loading the top few bits of this, it's kind of treating that as an address, and because all the data is at a very high memory address, it's loading this into the top 16 bits, and that happens to correspond to where X is located in memory. So this instruction, by the way, the MIPS instruction codes are all available. There's extensive documentation, so if you want to go and find out exactly what LUI does, you can go and have a look at the MIPS docker and it will explain precisely what's going on. Oh, sorry, in fact, this load address is actually these two instructions here. Okay, so we load a bit into the top 16 bits, and then we load some more stuff into the bottom 16 bits. And what was the intention? $A0, yeah, okay. So we load something into register 1, and then the contents of register 1 with the value A, and we store the result in register 4. And if you go back and look at the list of registers and the symbolic names, register 4 happens to correspond to $A0. So that's how you interpret all of that stuff. So load this 16-bit bit string into the top 16 bits of $1, then register 1, and register $1 happens to be that $AT register that I talked about, which is the assembly temporary register, and then take the value in $1 or 8 onto it. So you've got 16 bits up here, then you've got another 16 bits corresponding to the value 8, so it'll be lots of zeros, and at the end you'll have 1, 0, 0, which corresponds to, 1, 0, 0, 0, corresponding to 8. You'll stick those two things together. That'll give you a 32-bit address, which corresponds to the address of ask1. Okay? And then it will store that into $4, which happens to be the register A0. So one thing, it's going to be a lot easier to read this part of the code if you start to learn what all these register numbers are. So know that $4 is $A0 and so on and so on. Of course, you can always just look over here, which might be more useful. Who knows? Alright, so one thing we can do, we can run that code and it will pop up this console window, and voila, and then we can type in whatever I type. No, I'll type in something different. Oh, that's a good number. It actually helps if you type in something where you know what the result should be. So what should that be? Oh, let's make that 0. No. Oh, really? Backspace doesn't work. That's annoying. Alright, anyway, that's the final result of adding those two numbers together. The other thing you might notice in qtspim is that it's showing you all the registers that have changed. So if you're stepping through the code one instruction at a time, it will show you which register just changed. The other thing it's showing you here, I can get rid of that console, it's highlighting the last instruction that was executed. And this instruction here did syscall 10. Syscall 10 is effectively halt the execution of the program. Okay? So if we really wanted to, let's, do we go back to the start of the program, maybe? Nope, maybe I can just do that. Nope. I know what to do. And when you do that, PC becomes set to 0. Let me just reinitialize, reload, put the code back in. Alright, so it's all there again. And this little button here will let you execute one instruction at a time. No, it won't. Oh, damn, it runs. Lucky I didn't know this single step. Alright, so I jumped down to, why did I jump down to there? I should be at the start. Oh, interesting. Reinitialize, reload. Maybe because I accidentally executed. Alright, let's try that again. So it says PC 0, that's interesting. I would kind of hope, right, that's more like what I was expecting. So it executed that instruction there. This is the next instruction to be executed, and you can see PC is set to 4.04. So these first few instructions aren't doing stuff that's particularly interesting at this stage. So we come down to here and we do the jump and link instruction. Alright, what does that do? It transfers control to the main program, which happens to be at this address. So what we would expect to see happen after I execute that instruction is that this value will change to that value there. The other thing that I'd expect to see happen is the value in $RA, which unfortunately is right down here, so we have to scroll, will end up being this location here, which is the address that we're going to come back to. Right, so jump and link says, all right, where's the next instruction when I return from the function? It's here, and then transfer control to the function. So executing this, let's show PC. So that's current value of PC. It should change to that if I do a single step, which it does. And you can see that now we're at the first instruction of my main program code. I guess one thing that's slightly annoying about what what gets shown here is it doesn't show you any of the labels. So I don't know that this is the start of the main program, unless I happen to know, that I put the label main in my original MIPS assembler. Right, so it's transferred control to here. The other thing that I said would happen is that RA would get the return address, and so RA now has this value here. So when this function finishes and I execute the jump on register RA, I'm going to go back to that address there. Now that address happens to be a no-op, which means does nothing, and I'll explain why we have no-ops there later on. It's to do with the pipelining. Alright, so I can keep single stepping, I can load up something into R1, okay, remember that's, this makes it a bit clearer, so that's the AT register. I then do the OR, and that gives me a value in, hey, what happened to AT? Oh, it hasn't done it yet. Is that true?
Dr. Shepherd?
Yes.
So what is this list actually?
Which list?
This.
There's multiple lists. Alright, these are the memory addresses.
Yes.
These are the binary code that's stored at each of those memory addresses. These are a symbolic representation of that code, and this is the code, well, from here on down is the code that I actually wrote in MIPS.
Alright.
And this is the list of registers. Alright, so
Thank you, Dr. Shepherd.
yeah, so the OR instruction here is set up that address. So that should be the address of the ask1 function. The next thing we're about to do is load immediate 4 into $V0, which happens to be registered 2. So that should change, and we've got value 4 loaded up there. Next thing we do is we do the sys call, which is going to, doesn't pop anything up. That's slightly annoying. Oh, that's printf. Even so, it still should pop up the console. Where's the console? I don't know, maybe you don't get it in single step mode. Alright, maybe we get a console when we do a scanf. Oh, other things to notice, R2 now contains the value 5, which is the syscall code for readint. Alright, when you're single stepping it looks like you can't read, which is slightly annoying, but anyway, what the syscall eventually does is it loads the value that was read into the register V0, so it's put a 0 in there. And then we're going to store this value into the variable x. So the first thing we've got to do is produce the address of x, and you can see that we've got 4097, 4097. So we're going to calculate the value, the location of the variable x by doing this load upper immediate. Store the value out to the memory. Now if I actually had a non-zero value, I could go here and I can see the non-zero value that had been stored. But unfortunately I don't. Then load in the address of ask, so if I do a few more single steps, that's loaded in the address of the ask string. Then do a syscall, print out the string, then set up 5 to read in the next integer, read in the int, which doesn't work in single step mode, then store the value out into y. Since it's a 0, we can't see anything in the data segment. Load the value of x, which into register T0, which happens to be $8. So $8 got the value 0, not very helpful, is it? And so on and so on. So you can step through and see in excruciating detail what's happening, and it's better if you're not doing any reads, if you're just doing writes and stuff. It's probably easier to see what's going on. And I've gone too long, so let's have a break, and I'll do a short second part of the lecture.